Um, so let's start with today's lecture, which is finally about the Feynman rules for the simplest case of the lambda phi 4 interacting scalar field theory from the operator formalism. So as I said, the Feynman rules are the basis of perturbative calculations of the of quantum processes. And today we'll do that for the first time. We'll define them and use them to calculate things. So a reminder of what we did so far. So we have quantized the field, we can quantize three fields. Then we have considered interacting fields by using the Dirac interaction picture, in which we kept the quantization of the three fields, we found a way to relate. So we related the quantities that we were interested in, which were correlation functions of a full interacting theory. Time-ordered products of the field, of the Heisenberg operators for the field in the full vacuum of the interacting theory. We've related that with the Feynman theorem. We've related that with time-ordered correlators of the interaction picture fields, which from now on I'll define as phi, but really is phi I. In the unperturbed vacuum, and more precisely, I've considered these, but then also insertion of the exponential of the interacting Hamiltonian in the interactive picture. However, this exponent is of course just a sum of this factor to the n, product powers of this interacting Hamiltonian. And the interacting Hamiltonian in the interacting picture was only this whole thing, the integral of the interacting Hamiltonian was lambda phi 4, the interacting picture field, integrated over x. So this was at some position x, integrated over. So that means that really, and okay, so we had the denominator in the Feynman theorem was this divided by the same thing without the fields. So just the interacting picture Hamiltonian. And then there was some limit, t going to infinity, 1 minus I epsilon. Right? But the point is, the objects of the theory here are of the general form. Of correlators of, that is to say, expectation values in the unperturbed vacuum of time-ordered products of interaction picture fields. Because in here, by expanding this, I also get products of phi's. The only difference is there will be several phi's, in this case 4 phi's at the same vortex, but otherwise they're of the same type. And then finally we had the Wick theorem, by which we've calculated things like that. And we showed, so the Wick theorem was saying that the time ordered product was equal to the normal ordered product plus normal ordered product of all contractions. The contraction of field was equal to the Feynman propagator. And then all contractions means only complete as well as partial. Just that, when putting this in between vacuum, all non-trivial normal ordered products, the one that still have some operators inside, give 0. So we are in the end left with just equal to all full contractions. Okay, so that's what we did until now.
Professor?
Yeah.
Sorry, why are you emphasizing every time that the interaction part of the Hamiltonian has this form? Because we deduced this form of the Feynman theorem for any h of I, right?
Yeah,
right?
no, but I meant that it is.
Has this form.
Sure, but I meant that the interaction Hamiltonian is always a function of the fields, right?
Right, but
in this particular case, the case that we were interested in, lambda phi 4, has this form. I think always it will be whatever. I mean, maybe it has some derivatives, but or gamma matrices or whatever, but it's always a product of fields with some constants or derivatives. I mean, things that are, from the point of view of an operator, are constant,
yeah.
right? So that means that in the end, when you expand the exponential, you will only have things like this. I mean, here there might be other constants, but as a field, you only have things like that.
I understand that, but let me reformulate my question. What's that is so important in this type of interaction that you're emphasizing that much? Why do you have a chapter only for Feynman rules for this form of the...
It's just the simplest case, right? I mean, we will see later on how to generalize, but...
Because that's a restriction, right?
No, it's not. That's my point. That is not a restriction. It's just very easy to generalize, and when generalize, it's extremely obvious. Okay.
So you're taking an easy case, just we calculate you shorter.
Yeah. Okay. You have to take some example.
Yeah.
So, in particular, we have seen the simplest case of the 4-point function. So, well, more precisely, I should have said the 4-point function appearing in the calculation of some actual correlator, some correlator of the interacting theory. We are considering this interacting picture 4-point function. And I've seen last time that there's a bunch of normal order products, many that cancel in the web. And then we're left with just the full contractions, which there are 3 terms. So first we have this contraction, which is Feynman propagated x1 minus x2, x3 minus x4. Then we have this contraction, so Feynman propagated x1 minus x3, x2 minus x4. And then we have this contraction, x1 minus x4, x2 minus x3. Okay, so this was the full result using the weak theorem. And now, as a first step, we make a diagrammatic representation of this. So we say, well, we have 4 points, let's say And so these are the 4 points in the 4-point function. And these terms correspond to various ways of connecting them. So the first term is this way of connecting them, 1 with 2 and 3 with 4. The second is 1 with 3 and 2 with 4. And finally, we have 1 with 4 and 2 with 3. Okay? And then, at least in this case, we will call this a Feynman diagram. These are Feynman diagrams. Each of these is a Feynman diagram. We see that the logic of this is I wrote the 3 external points, the 4 external points, and then I connected them pairwise in all possible ways. Right? So there's a simple pictorial representation. However, at this point, what we're drawing here is not exactly physical. I mean, I said that the correlation function or endpoint function is, has, on some conditions, has some interpretations, like in condensed matter, correlations of quantities in different points in the material, or in cosmology, correlations of variables like temperature fluctuations in the sky. But the case where this arose first, where Feynman was concentrated on first, is the case of particle scattering. So the Feynman diagrams, in principle, are meant to describe propagation of particles. Just that at this point, we are not doing that. At this point, the correlation function is not itself describing a scattering. So, as I said, again, correlation function does not represent particle scattering, but rather is related to it by the LSZ formalism. So the LSZ formalism that we'll come to later in the course will relate correlation functions with scattering amplitudes, which truly represent scattering of particles. Really amplitudes for scattering of particles. But for the moment, this must be thought as somewhat more abstract. We still have in the back of our mind particle scattering, but for the moment the interpretation is not so clear cut. Okay. So let's move. So this was this calculation was if we want a 0th order result, in the sense that there were no interactions. Right? Particles propagating freely without interacting with each other. And I just showed to you that there were in principle 3 ways for them to propagate freely. From 1 it could go to 2, or to 4, or to 3, and then the other one in between remaining. Now let's see what happens when you consider interaction. As I said, when you expand this thing, we will have powers of the interacting Hamiltonian, therefore coming with the interacting coupling constant for this interaction, lambda. And let's consider the interaction at first order, lambda. expand this exponential and consider only the linear term. Term is n equals to 1. And moreover, the simplest case that we'll consider now is for the 2-point function. So we consider two external points, phi of x and phi of y. And then from the exponential, here we'll have exponential, but let's consider only the linear term. Okay? And as I said, this thing is itself equal to d4, let me call it z, lambda over 4 factorial, phi to the 4 of z. Okay? So, what I mean by this is t phi of x, phi of y, minus phi lambda over 4 factorial, integral d4z. Now, I'll write this explicitly as phi of z 4 times. Okay? So, I have then 6 z's in here. I have 1 phi of x, 1 phi of y, and 4 phi of z's in this object. And as I reviewed from last time, we know that the result of this is only full contractions. Okay? So we have to consider all the full contractions of these 6 fields. All full contractions of the 6 phi's. Okay? But if you think about it, you see what kind of contractions you can have. Well, you can easily convince yourself there are only 2 independent contractions and the rest are identical. They are just permutations of this. That is to say, I can either contract one of the phi's with one of the special phi with the other one, and then these ones among themselves, or one of here with one of here, and this one with another one of here, and then the remaining ones. So I have only 2 independent ones. Okay? So one would be the contraction of phi of x with phi of y, and then the phi of z's among themselves. Right? And the other one, let's say phi of x, phi of z, one of these, phi of y also, phi of z, because there's nothing else remaining. And then phi of z's, remaining phi of z's among themselves. Right? But how many terms there are in total? Well, so for this thing I have only one choice, right? For this thing I have only one choice. But then I pick one of the phi's, and I have how many? 3, right? I can choose to contract either of these 3. And once I do a contraction, I'm left with 2, which have to be contracted. So here I have 3 terms. Now, for this other contraction, let's say phi of x, now I have a choice of 4 possible phi's to contract with. So that's 4 possibilities. And then I pick up one, so I'm left with 3, and phi of y then has 3 choices. Right? So in total, I have 4 times 3, that's 12 terms. that the sum of them is 15. Which is the total number of possibilities I would have, because I have 6 phi's. Okay, so for the first contraction I have 5 possibilities, one with one of the other 5, and now that I picked 2, I'm left with 4. So the next one has 3 possibilities, and then the final one has only 1 possibility. So all in all, there are 15 terms. Okay, so the counting is right. We have all the possibilities. Makes sense. Okay. Good. So then let's write the result of this. So let's say that our result for phi of x, phi of y, then minus I integral dt, h I t. The result for this is, well, we have the term minus I lambda over 4 factorial. And then for this contraction we have a factor of 3. And then the propagators are df x minus y, df z minus z, df z minus z. And then for the second we have 12 terms times this factor minus I lambda over 4 factorial. Then df x minus z, df y minus z, then df z minus z.
Do you have need to go over before this?
Right, thank you. Yeah. So this was all integrated before C. Okay? Good. Alright, so let's see how can we represent this. So we saw already that we wanted to represent the Feynman propagator between 2 points by a line between the corresponding 2 points. And we also saw that there were as many external lines, external points, as many as these independent phi's. So in this case we have 2, right? We have 2 independent points, x and y. And then we have what? So this term is a propagator between x and y. And then we have, so maybe I should put this separately for each term. So just to see that in this first term, the propagator is outside, but then there's this integrated over z, which has 2 propagators from the z to z. So this is times, and I put this z integrated over. It has 1 propagator from z to z and another from z to z, right? And then in the second term, I go from x to this z to be integrated over, and then from z I go to y, and I also have another propagator from z to z, right? So this is my second Okay. So this is what happened at first order. Now, as we increase the order, things will get much more complicated. So I will not write all the diagrams from now on, but I will describe for you one contraction and the corresponding phi-1 diagram that is a bit more complicated, just in order to emphasize all the possibilities that we can have. Let's say other contractions and diagrams. So my example will be an order lambda cube term. That is to say, in e to the minus I integral h, I will consider the cubic term. So from this, I will take the term with 1 over 3 factorial minus I h integral h cubed. Okay? This each of these h's has a lambda, so this term will have lambda cubed. Right? So corresponding term, and I'm still considering this in the 2-point function. So I still consider just phi of x and phi of y, two external points. But now I consider the cubic term in the interacting Hamiltonian. So 1 over 3 factorial, and minus I lambda over 4 factorial cubed. And then let's write 3 times the interacting Hamiltonian with integral integrals over z, w, and u. So phi of z, then phi of w, and phi of u. Okay, so I consider this term, and moreover now this term has many contractions corresponding many Feynman diagrams. I will not write them all because there are too many. One could, perhaps, if you want to do it yourself as an exercise. But I'll write one of them to show some new features relating to combinatorial factors. So let me consider the following contraction. So let me consider a contraction of a phi with a z with a z, a z with a w, two w's with u's, and u with a u, and then w with y. Okay. So this is a particular contraction among the many total contractions possible, and the result of this contraction is what? Well, first of all, yeah, let's write the combinatorial factors outside. So 1 over 3 factorial, then minus I lambda over contraction gives a finite propagator. So, Z minus W, Z minus Z, sorry, X minus Z, and X minus Z, the first one, then Z minus Z, then Z minus W, then W minus U, one more W minus U, then U minus U, and finally W minus Y. Okay? These are all the contractions I wrote on the board. And now, to write the corresponding Feynman diagram, we know that there are two external points, and then we know there are three internal points, Z, W, and U. Okay? But Z is connected to external point and W is connected to external point, whereas U is not. So let me write it like this. So Z connected with what? With X. Then W is connected with Y, but U is not. Okay? So for the moment I don't know what this does. But next I see, so I've written this, I've written this. Next I write Z with Z. Then Z with W. Then W with U. So it looks like this U has to be here, but twice. So once like this, one like this. And then finally U with U. Okay? So that's the Feynman diagram corresponding to it. Okay? However, the point about writing this complicated diagram was to see the combinatorics. Okay, so let's see what combinatorial factor multiplies this diagram. Okay, so let's say combinatorial factor. First of all, I have three integrals, okay, and I have to, one way to define it would be to say that, let me define Z to be the one contracted with Y, with X, W to be the one contracted with Y, and U the other one. So that means that out of these three integrals, I have three factorial ways of choosing Z, W, U, right? Then, once I do this, I have, so I've defined what Z is, and I know then that X has to contract with one of the Z's, but which one? I have four choices, right? So I have four choices of phi of Z. Contract phi of X, right? And then let's say, that I also want to finish with this Z. So I want to contract one of the phi's with one of the phi of Z with one of the phi of W's. And then that means I have a choice among the three remaining phi's. So I can choose 3 choices of phi z with phi w. And then the remaining phi's are contracted with each other. Right? But then I still have 4 choices of phi of w in here. So I chose 3 out of phi of z. I still have 4 choices of phi of w. Choice of phi of w. This thing. And then 3 choices. 3 choices, let's say, 3 choices to contract with phi of y, right? 3 choices, phi of w, phi of y to phi of y. Okay, so the 3 choices are this contracting with one of the remaining 3 phi of w's. And then I have 2 choices of which, so I'm remaining with 2 phi's, but out of these I have to pick one that will contract with one of these guys, and then the remaining one is fixed. So 2 choices of phi of w to phi of u, okay? And now, finally, on the other side, on the side of phi of u, I can choose the first one I picked, phi of w, to connect with one of 4. So I have phi of u. I have 4 choices. And then the remaining one in here, the remaining phi of w can be chosen with 3 possibilities, because I have 3 remaining phi's. Remaining phi of u, phi of w. Okay, and then the final thing between u and u is a factor of 1. However, you note that if in this counting, I said one phi of u contracts with phi of w, and then one phi of u contracts with another phi of w. So these 2 things are actually equivalent, right? So I overcounted twice by doing this, because I did this as if these 2 contractions were somehow independent and I can define one and the other, but I can't. They're equal. So I overcounted a factor of 2, because phi of w, phi of u, because the 2 phi of w, phi of u contractions are identical. Okay? Alright, so let's now write the full answer for this. So the symmetry factor for this diagram, the combinatorial factor I should say for this diagram. So combinatorial factor of the diagram is, so I have first of all 3 factorial times, this was an overall thing, then from phi of z I have 4 times 3, and for phi of w I have 4 times 3 times 2, And finally, for phi of u, I have 4 times 3. And then there's 1/2 division. This, then comes 4 times 3 times 4 times 3 times 2. And then I can do times 1. Write this as 4 factorial if I want. And then the last one is 4 times 3. And then I have a 1/2 for the overcounting. Okay? Good. But you see what happens here. I get almost 4 factorial 3 times, because this is 4 factorial over 2, and this is also 4 factorial over 2. Right? So this is 3 factorial times 4 factorial cubed divided by 2 to the 3. Okay? So note what has happened. This is almost almost entirely the factor by which I divide. So there was 1/3 factorial coming from the expansion of the exponential. And then 4 factorial cubed, because this was order lambda cubed, and each lambda I can put with 1/4 factorial, having in mind that this will happen. Okay? So this almost cancels. 1/3 factorial, 4 factorial cubed. The only thing that doesn't cancel is this 1/2 to the cube. So only remainder is 1/2 cubed. And this goes by the name of symmetry factor. We'll shortly see why. So the symmetry factor is by definition the denominator, meaning this 3 factorial, 4 factorial cubed, divided by the number of contractions. In this case, this was 3 factorial, 4 factorial cubed, divided by 2 to the cube. So in this case, this is 2 to the cube. Okay? And you see, I said here 3 factorial, 4 factorial cube, but you note that this, if I had expanded, excuse me, if I were looking at the order lambda to the p term, so expanded to order p, in general, this would have been p factorial, 4 factorial to the p, right? Where p is from order lambda to the p. Okay? So if I consider the order lambda to the p term, I would get the denominator would mean p factorial times 4 factorial to p. And also 4 factorial is just because I choose lambda phi 4. If I choose lambda phi n, it would be n factorial. Right? That's kind of clear, I suppose. Okay, so why is this called symmetry factor then? Why is this 8 to cube is symmetry factor? Where does this come from? Well, let's see what are we missing, right? So there's a 2 factor missing here in phi of z, and there's a 2 factor missing in phi of u, and then there's also a 2 for interchange of the contractions with phi of u, between phi of u and phi of w. Okay, so there's a factor of 2 connected with the interchange of contraction between phi of u and phi of w. There's a factor of 2 connected with Z, or in other words, with the self contraction of file Z, and there's factor of 2 connected with U, which is to say with self contraction of file U with file U. So now we figured out why this is called a symmetry factor, because this factor counts the symmetries of the Feynman diagram. Let's write this here. The symmetry factor counts the symmetries of the Feynman diagram. So my identifications here tell you that I can interchange these 2 lines, right? I can switch them like this, and the diagram remains the same, right? Then here, the same thing says that I can switch. Switch the 2 lines of the self-contraction U, and again nothing changes. And here I also can switch the lines of the self-contraction Z, and nothing changes. Right? All right. So once we've seen this, let's do now a few more diagrams. And now without doing all of this contraction and counting, because now we assume that this formula is correct, that the symmetry factor really counts the symmetries, and then we see what we get. I mean, I hope that I convinced you in this way that you actually are supposed to get the symmetry factor, but let's see specifically. So let's consider first this diagram. So what's the symmetry factor here? 2, right? I mean, it's just one example of this thing that I showed you. I can switch this thing. The symmetry factor here is 2. Okay? Then the figure 8 diagram. That's a vacuum diagram from the denominator of the correlator, where there are no external points. What's the symmetry factor here? Sure. 8. So the point is, we do have this, which is probably why I said 4. But now I can also do this, right? I can interchange the 2. So this is 2 times 2 times 2 is 8. Then, let me consider this diagram, also called the setting sun. Probably by some Japanese. Anyway, so what's the symmetry factor for this? Well, so what do we are supposed to interchange in here, do you think? The lines, right? But there are 3 lines, right? Now they're not 2. Here there were 2, but now there are 3. And it doesn't matter how I interchange them, I still get the same thing. So this is 3 factorial, right? The interchange of 3 lines. So that's 6. Then I can also consider, for instance, this diagram. What's the symmetry factor of this? Well, so at least part of it is the same, right? I see the same blob in here. So I can have the interchange of these 3 things. if I flip, perhaps not, but yeah. I mean like this, I take this and I flip it completely, you see? Right? If I do this, I get an extra factor of 2. So this is 3 factorial times 2. That's 12. Okay. All right. Good. So I've told you what the symmetry factor is for these Feynman diagrams, and I've shown you how to draw the diagram. So now let's actually define the Feynman rules. We're ready for that. So let's say X space Feynman rules for diagram 5, 4. So we have been considering this numerator, but in fact, if I just don't put any, if I put n equal to 0, so no external points, I also get Feynman rules for the denominator. Right? So minus I for this thing. So first of all, what do we see in this? In these diagrams? Well, we see 3 kinds of things. We'll see some internal lines between 2 points. So somehow this thing must be a propagator. I mean, we saw that from the most basic term, the 0 for the term without any interaction, we saw that we obtained contractions that were giving the propagator between 2 points. So that's clearly one thing. Then there are some factors associated with these vertices, right? So we denote by this intersection a vertex, and then we'll see what we get. And another thing in principle, in here was not obvious, but we'll see in momentum space shortly that it's a little bit more obvious, that if I have some external points, like x and y in here, there will be something associated with them. Alright, so then let's write the Feynman rules. So for the propagator, draw a line between x and y, and the corresponding value for it, so corresponding to the Feynman propagator, right? Then for the vertex, draw a point Z with 4 lines in this case, because we have interaction of 5, 4 coming out of it. this corresponds to, well, these vertices were internal points, all of them, right? They were not external points, obviously. And so they came, first of all, with an integral over them. And then, these are things at which we have an interaction Hamiltonian, right? So in this thing we have three integrals, each integral coming with a factor of minus I lambda, right? So that means this has to correspond to minus I lambda times this integral. Okay. And now this thing is kind of trivial here. So, but we'll write it anyway. So, for an external point, draw a line ending at x. And then, in this case of x space Feynman rules, for the correlator, the external line is just 1, there's nothing. But in momentum space, we're finding a non-trivial thing. And then, we're not done. We say, so we draw the Feynman diagram. And then divide by the symmetry factor. That are called S. And then sum over all diagrams at the given order in lambda. Remember, lambda, the interaction, which is governed by the counting constant lambda, is supposed to be small. We're doing perturbation here. So that means I consider things order by order in lambda. So at each order in lambda, I do this. It's not necessary. In principle, I could say, well, I write all possible diagrams. But in order to do perturbation theory, I have to order things by powers of lambda. Okay. Let's consider now momentum space. The same thing in momentum space. So we found that we had three objects in here: the propagator, the vertex, and the external line. So let's see what happens in momentum space to each of them. So the Feynman propagator, we calculated it as an integral of momenta, and we saw that it was this, right? We calculated it to be this. So we see that this is just a Fourier transform. So we can immediately write that in momentum space, df of p is just minus I over p squared plus m squared minus I epsilon. Okay? So this is the propagator in momentum space. But there's one thing here. Momentum is something with direction. So we have to choose a direction. df of x minus y equal to df of y minus x, right? Because if I choose y minus x, I get just a minus sign in here, but then I can interchange p to minus p in the integral. Here I have d4p, so that's even, and here I have p squared, so that's also even. So I get the same result, right? So df of x minus y is equal to df of y minus x. So that means there's no preferred direction. I have to choose a convention, and I choose to go from x to y. It's just a convention. It's only because the momentum has a direction, so I do have to choose a convention. But then, I consider just this propagator, so the zeroth order term for the 2-point function. That would be just a propagator, a single propagator, right? And so the expression for this is this thing. So now I see that I have something associated with the external line, right? I'm in momentum space, but then I have a factor of e to the I px associated with x, and so I've chosen my direction to be this one from x to y, and then I have e to the I px associated with x and e to the minus I py associated with y, right? So I mean that so then external line, if the external line is for line going into x, then the factor is y perhaps, just to be more obvious with what I wrote over there. I will have a factor e minus I py, okay? And then, what about the vertex? Right? So, I have a point Z, and let me assume that I have P1 going in, P2 going in, P3 going in, and then P4 going out. For instance, this, right? So vertex is something with, like this, with 4 lines and the point. But the point is in the middle, so it's integrated over. So I have D4Z. And then, for this, each of these lines, I have such a factor, right? So I have e to minus I P1Z, e minus I P2Z, e minus I P3Z, then e plus I P4Z, because P4 goes out. So this is, of course, e to the I Z P4 minus P1 minus P3. This is symmetric, I can put a minus sign if I want to, so I want to write this as 2 pi 4 delta 4 P1 plus P2 plus P3 minus P4. Okay? So this is the vertex factor appearing for this vertex. Okay? This is, of course, momentum conservation. we know is supposed to be true. So this is momentum conservation at some internal point z. Alright, so let's write then the didn't plan correctly. I wanted to leave the X-space rules, but whatever. Let me erase and write the P-space rules. So, for the propagator, we write a direction, a line with an arrow. In the direction of momentum, corresponding to the propagator EF of B, right? So in this case, the propagator will be something like this. Then for the vertex, write 4 lines going into a point. So note, I can flip this. Here I put just for simplicity, but if I flip this, I'll get all momenta with the same sign. And this is usually the convention one uses. I could use the opposite convention, but all momenta going in. So corresponding, so this is a momentum conservation, so I can consider it as part of the vertex or write it as a separate Feynman rule. But in either case, I do have this factor minus I lambda. And then let's say impose momentum conservation at each vertex. It's 2 pi for delta for something like pi. Okay. Then for the external lines, write an arrow going into a point. Point x, corresponding to e to the minus side ex, right? And then, well, similarly to here, to X space. So in X space, I had to integrate over internal positions. Now I have to integrate over internal momenta, right? So integrate over internal momenta. Divide by the symmetry factor, and then the same thing. Write all Feynman diagrams, sum over then for the lambda. one observation about the Feynman propagator. So, of course, the Feynman propagator was obtained within the Feynman theorem. Within the Wick theorem. When calculating time-ordered products, the non-zero thing was just a contraction, which was given by the Feynman propagator. But now you might ask, was this natural considering the Feynman theorem? So let's see, because a priori is a different kind of theorem, right? So you might ask yourself, is this, was this a good choice? So let's ask like this. Was the Feynman propagator a good choice from the point of view of the Feynman theorem? And the question is not without merit, because remember that in the Feynman theorem we were forced to take a limit that was somewhat special. We took the limit where time goes to infinity 1 minus I epsilon. Right? This limit was needed in order to relate the correlation function in the full theory with the correlation functions in the interacting picture. So, the question now is this consistent with this limit? Because you see, things go to infinity, but in a particularly regularized way. So the Feynman propagator corresponded to this contour, or another way of saying it, the contour was slightly off, right? It was linear but slightly off. And this came because we had P0 going like 1 plus I epsilon. But then at some point Z, we have these P1, P2, P3, P4 going in, right? So we actually have, so I wrote integral over d4z, but really time, remember, was finite, going from minus t to t, and we took the limit afterwards of this t being going to infinity in this way. So t goes to infinity times 1 minus I epsilon, but then in such an integral over t, let's say dz0, this is, then I would have something like this. And the point is, so in particular in here I would have z0 p1 plus p2 plus p3 plus p4 0. And then t itself is 1 minus infinity times 1 minus I epsilon. here the two endpoints are t and minus t, right? The endpoints are t and minus t. And in fact, in here I have plus or minus, right? So, and here I have an I in front. So, all in all, I get plus or minus I infinity 1 minus I epsilon times this P1 plus P2 plus P3 plus P4 0. So you see, because the integral is from minus t to t, I cannot choose, because I have to consider both endpoints. So I cannot choose the sign in here. And then this I times minus I gives plus. So this will give a term plus minus infinity epsilon P1 plus P2 plus P3 plus P4 0. Okay? So this would blow up somewhere. Right? It's just that, so if the p's would be real, if the integral in other words, if the integral in the propagator would be completely real, then this would blow up somewhere, either at plus t or at minus t, and that would get infinity. Either plus t or minus t. But the essential point is that now I have this 1 plus I epsilon factor, right? So, more precisely, I have it here. P0 comes with P0 comes with 1 plus I epsilon. That's the meaning of this line. The contour can be thought of either this or more precisely this. It's slightly tilted by 1 plus I epsilon. And that means that actually I have 1 minus I epsilon, 1 plus I epsilon. Okay? And then this itself is 1 plus order epsilon squared, right? The order epsilon terms have cancelled. And the epsilon squared is negligible. I mean, that's the point about this epsilon expansion. I'm supposed to keep only the linear terms, right? And then this is now multiplied by I. Okay? So by I is fine, that's an oscillatory thing that doesn't give you problems at infinity. So I avoid the problem. Okay? So the Feynman propagator was the correct propagator to choose, having in mind this limit from t going to infinity 1 minus epsilon that was necessary in the Feynman theorem. Okay, so that's a good consistency condition, because otherwise the Feynman propagator was obtained just from the V theorem, which was independent by calculating things, so it was not guaranteed from that itself that we would get finite results. Now we know. Okay. Then the next thing to see, actually the last thing to see, is that so I've calculated for you terms in the numerator of the Feynman theorem. And I said, well, in the denominator we have the same things, just that we don't have external points. Right? So in the denominator, that means that we have in the denominator we have things that don't have external points. So there are things like this, which are called vacuum bubbles. that we will see now is that these vacuum bubbles cancel between the numerator and the denominator, giving only Feynman diagrams without such bubbles. So let's say cancellation of vacuum bubbles in numerator and denominator of Feynman theorem. Okay? Well, first of all, why would these vacuum bubbles be a problem? Well, let me take one example to see what we get. And I'll do the calculation momentum space since later on when talking about scattering amplitudes, it's more natural to consider momentum space. Particles have given momenta. So let me define, say, momenta as P1 here, P2 here, P3 here, and P4 here. Okay? So this is a vacuum bubble. And let's write the corresponding Feynman diagram, the value of the Feynman diagram. Well, so I would have conservation at each of these 2 points, right? So you see, P3 goes in, goes out, and then goes in. So that cancels. We will obtain P3 minus P3. So momentum conservation here, actually, I chose this wrongly. We choose it like this, so both in here and both out here. So then I would have 2 pi 4 delta 4 P1 plus P2, momentum conservation here. Right? And then momentum conservation at this other point would be 2 pi 4 delta 4. Now it's minus P1 minus P2, but that's the same. P1 plus P2. And P4 the same thing, goes in and out, so it's P4 minus P4, that cancels. So I get one more of these things, right? And of course I have an integral okay, I have an integral over, let's say, P1. And then, of course, also an integral over P2, and so on, and P3 and P4. But for the moment, I don't care about this, because, so that in principle also has its problems, but I see the problem already by doing just this integral, right? Because by doing this integral, I do the integral over P1, right? And that makes P1, so the integral makes P1 plus P2 equal 0, right? In other words, P1 equal to minus P2. But then, that means so this is from this delta function, but then I have to substitute everywhere, including in this other delta function. So here, I have to substitute that P1 plus P2 equal to 0. Right? This, when I do this, I kill the delta function, that's the definition of delta function, but this is on top of it, right? So this is already 2 pi 4 delta 4 of 0, which is infinite, right? And then, of course, I also have these other integrals, which also in principle give infinity, but I already have delta of 0, okay? So, to be in X space, I would have I would have an integral over W of something that doesn't depend on W. So I would get an infinity from space, infinity in space and time, right? So it will also be infinite. So the point is that all of these vacuum bubbles are infinite, right? So if they wouldn't cancel, we would have a problem. We would just get infinite results. We wouldn't know what to do with them. But luckily, they cancel between numerator and denominator, and we're left with, well, less infinite results. So we'll still have infinities, but ones that we can deal with. Okay, so the unphysical infinities cancel out between numerator and denominator. So let's see that. So of course, how can they cancel out? It means that, in the denominator, we only have these vacuum bubbles because we don't have external points. But that means that in the numerator, they must factorize, and they will also exponentiate. So vacuum bubbles factorize and exponentiate. So let's see that. Okay. So let's see this with an example. Let's consider the two-point function. So we will have in the numerator, we'll have the limit t phi of x, phi of y, e minus I into 1 minus t, h by I, t. But let's see what kind of things are we supposed to get. So what we'll get? Well, we'll get, in the two-point function, we'll get some connected piece. For instance, the setting sun. The setting sun has lambda here and lambda here, so this already contains two interacting Hamiltonians with the corresponding contractions. But then, besides this connected piece, in principle, then there can be some disconnected piece. That is actually a vacuum bubble. So I can have what? Well, at order lambda, I can have this, right? I have one external point, and then I can have self-connection between then at order, so this is at order lambda, then at order lambda squared, well, I can have two of these things, right? And perhaps more. So in principle, I could have, let's say, also this, right? Then at order lambda cubed, I can have, for instance, products of these things. And other things. Okay? This was already order lambda squared connected diagram. And let me call this independent diagram V1. And this one V2. This is an independent order lambda diagram. This is an independent order lambda square diagram. Okay? And you see, I have, I see that I have a certain pattern. So in this result, I have a connected piece. Times, then what do we have? Well, I have sums, so I have like this plus this plus this, but in each term, in principle, I can have, so this is V1 times V1, this is V1 times V2 times V1 times V2, and so on, right? So in this, in each such term, I can have products of these independent diagrams. Okay, so let's say Vi to a number Ni, right? Like in here I have V1, here I have V1 squared, right? But products of these things, so pi over I, and each one of them comes with a symmetry factor of 1 over permutations possible of those of them, right? And then I sum over all possible sets of these ni's, right? So okay, here I have V1, V1, V2, so N1 is 2 and N2 is 1, right? And so on, right? N1 is 2, so for V1 I have power 2, for V2 is power 1, and so on, right? But then I can, since this is a product, so sum of a product is the same as the product over the sum of independent things, right? So this is the same as, let's say, the product, where I write sum of N1, but here I just write a single one, V1. So the product is over I, right? So, but I take the product outside, then in each I have sums, but only over corresponding n. In this case it would be N1. So Vi to the N1 over N1 factorial, right? And then sum over N2, V2, N2, N2 factorial, and so on, right? So to write this more specifically, it would be product over these i's with sum Ni 1 over Ni factorial Vi the Ni, right? are connected vacuum bubbles, right? This V1 and this V2. They're all connected among themselves, right? They're fully contracted and connected, but they're independent ones. But you note that each of these factors is an exponential, right? E to di, right? And the product of e to di is e to the sum of di, right? So that means this is equal to the connected piece times e to the sum I di. And I gave you one example of this, but for each connected Feynman diagram, I still have always the same product, because these are all the possibilities of bubbles, of vacuum bubbles, right? All the possibilities that are connected just with each other and not with these parts, right? So all in all, I have that this object, the object in the numerator, is equal to, so now I have all the possible connected diagrams. So let's say at order lambda 0 I have this, at order lambda I have this, and then at order lambda squared I have this setting sun and perhaps more, and so on. So all of these things times the exponential of the independent connected pieces. Independent vacuum diagrams. Right? So independent means these things that were connected with each other, but they are vacuum diagrams. Sorry. I also have this. So lambda squared, and so on. Okay. But now you immediately see that the same thing happens in the denominator. In the denominator, I don't have these things, so I don't have the connected piece. Right? I just have the vacuum bubbles, which will exponentiate this way. So let's try this. So denominator del 5x del y means no connected piece. But vacuum bubbles still exponentiate. In the same way. Right? So we can say then that limit more formally. So we have that this was equal to connected piece times this, and then limit b minus psi epsilon 0. Just this is just equal to e sin of I di. Okay? So the two exponentials cancel between the numerator and the denominator, and that means that the final result for the 2-point function is just a connected part, the connected diagrams. Okay, so you can say that only connected diagrams. And that of course generalizes, I said 5x, 5y, but of course generalizes to any n-point function. So this is the last part of the Feynman rules. So the Feynman rules for this contain also sum over only connected diagrams. Okay. All right. So this was the end of the discussion of Feynman rules in the operator formalism. That's all I wanted to tell you today. Do you have questions?
About that matter of sides having to circle or only connected, they also have to be unamputated.
No, that's for S matrices. That's
okay, that's only for S matrices, okay.
We'll get to that.
Okay.
All right. So the Feynman diagrams for correlators are the ones given, where I only sum over connected diagrams. All right. So this is it. For exercises, I'll give you to write some Feynman diagrams. So hopefully that should be easy, but well, we'll see. All right. So please give me exercises.